Good afternoon, friends. So I welcome you today. I am Rishikesh Misra, and title of today's lecture is Introduction to Radioactive Waste Management. Slides. So first of all, I wish you all Merry Christmas and Happy New Year 2024 well in advance. And welcoming you to the nearly end of our stage one program of the course on disaster management challenges in CBR and emergencies. So topics that we will be covering today in the lecture are nuclear fuel cycle, types of nuclear reactors, radioactive waste, waste treatment, decontaminations. We'll touch upon these subjects because I thought they are relevant for the course, mainly when we talk about the waste treatment, radioactive waste. We should know something about the nuclear fuel cycle, the types of nuclear reactors we have in our country or abroad, before we talk about the decontaminations. So I will touch upon those topics very briefly. And incidentally, this subject we'll be discussing in the stage 2 also. So partly only I will cover radioactive waste in today's lecture. The distinct other two parts will cover separately in the stage 2 sometime in February 2024. Nuclear fuel cycle. So it has 3 stages: front end, utilization stage, back end. Basically, these stages are defined with respect to the fuel. So nuclear fuel is to be mined, milling, converted in the useful form, and the fuel fabrication. These are considered as the front-end activities. The nuclear fuel, when it is utilized in the reactors, that is called utilization stage. We have research reactors or the nuclear power plants for generation of electricity. The nuclear research reactors are basically used for research and studies in the nuclear science, the material science, radiation shielding, and for production of radioisotopes. The backend activity, that is after the nuclear fuel is utilized in the reactors, it is considered as the spent fuel, or it is removed from the reactors as spent fuel. And the spent fuel is to be stored. So storage of spent fuel, the reprocessing for extraction of useful components, materials, useful materials, the waste, whatever is left over, the waste management, and storage of the radioactive waste. These activities comprise as part of the backend activities. I thought we should also see what is nuclear fission or nuclear fusion when we are talking on this subject. So the heavy atoms like uranium, basically uranium-235, plutonium-239, or even uranium-233, when they are bombarded with neutron, the fission reaction takes place. these atoms get split into the lighter atoms, and in the process, massive energy is released as heat energy. So this action is called nuclear fission. The opposite is called the nuclear fusion, wherein the lighter two elements fuse together and form a heavier single atom. And in that process, also massive release of energy, heat energy takes place. That process is called nuclear fusion. Nuclear fusion will not be covering. We will talk about the nuclear fission in this lecture. So as I said, the nuclear fuel cycle, the life cycle of nuclear fuel, starting from mining of ore, fabrication of fuel, irradiation or utilization in nuclear reactor, and then processing of spent nuclear fuel, SNF. That is the life cycle of nuclear fuel. The front-end activities, mining, you may be knowing perhaps that I will do changing from here. So as you would be knowing perhaps that at Jadugoda, Jharkhand, we have the mines for uranium. Excuse me. And it comes in the ore farm. It is said that we have much more abundant source of uranium than the silver, but basically problem is that uranium comes in the form of uranium-238. Natural uranium, mostly it comprises of uranium-238. And uranium-235 is the fissionable material. That is the fissile material. U-238 can be fertile, but to begin with, U-235 is important for us. So that is very, very small. I mean, that percentage is only 0.7% in the total uranium, natural uranium, whatever we can extract out from the ore. So the operation of extraction of natural uranium from the ore is called the milling. And then it needs to be converted in the proper form. That is, if we have to go for enrichment, it has to be converted as UF6, uranium hexafluoride. Or if we have to use it as natural uranium as a fuel for our PHWR reactors, then this is to be converted as uranium dioxide. So that is conversion, then enrichment, if applicable for reactors like light water reactors, the fuel fabrication, the front-end activities, the utilization stage reactor, and back-end is storage of SNF, spent nuclear fuel, reprocessing, waste management. The reprocessing, actually this spent nuclear fuel or spent fuel, we'll call it spent fuel, is not really fully spent because in the reactors, only very small percentage of uranium is used in the reaction. Thereafter, it is discharged from there. So we will be able to recover the unutilized portion of the uranium, and plus in the reactor, uranium-238 gets converted into plutonium-239, which is a fissile material. So we can extract out that plutonium-239, uranium-238 from the spent fuel. That operation is called the reprocessing. So fertile material is the material which is not fissionable. but that can be converted into fissile material by irradiation in reactor, like uranium-238 gets converted into plutonium-239, or thorium-232 that gets converted into uranium-233, which are both fissile material. The reprocessing process is known as PUREX, plutonium uranium redox extraction. And when the spent fuel, thorium-based spent fuel is to be taken up for reprocessing, the process is called thorax. The waste management is another activity under backend, and that is very useful for recovery of the minor actinides, which are present in the waste stream, which is called raffinate. And minor actinides are neptunium, americium, curium, and so on. We'll talk about this HLW, high-level liquid waste, which contains nearly 95% activity, radioactivity. We'll talk about that in our lecture of stage 2. So this is the nuclear fuel cycle, one pattern diagram, which is mostly applicable for the light water reactors. We have light water reactors at Kudankulam, but mostly abroad light water reactors are used. So uranium is mined and then milling, it is taken as U3O8, then sent to conversion as UF6, taken for enrichment, then fuel fabrication, the utilization reactor, then storage. After storage, either it can be taken up for reprocessing or it can be sent for direct disposal. After reprocessing, the plutonium can be taken up for reutilization as MOX fuel, mixed oxide fuel, and reused in the reactor. And uranium, whatever we extract out, can be sent here for enrichment. And in the mining process, whatever materials are left out after extracting out the U3O8, it is whatever remaining portion is there, that is referred as tailings. This is the nuclear fuel bundle. This bundle is also very, very specific to type of the nuclear reactor. Our 220 megawatt PHWR reactors use this type of bundle. That is called 19-pin fuel bundle. That is just to give you an idea. Now, nuclear fuel cycle, basically there are different types of fuel cycles in practice in the different countries. So open or once-through fuel cycle, the nuclear fuel is used in reactor only once, then discharged to interior storage, that is at reactor or away from reactor facility, until the decay of short-lived radioisotope, and finally to be disposed of into a deep geological repository at a later stage, or to be reprocessed. This is practiced in USA, UK, and South Africa. So meaning is that nuclear fuel, whatever you have, you are using it only once. After removing it, discharging from the reactor, you are directly storing it for a long time and then discharging into the repositories, or maybe at a later future date, you will take up for reprocessing. So it is called open-ended once-through fuel cycle. Just a note that light water reactor, which are there abroad or we have at Kodamkulam, the fuel is called the LEU, that is lightly enriched uranium, because it is enriched to the extent of about 3 to 5%. As I mentioned earlier, the natural fuel, natural uranium, contains only 0.7% of U-235. So that has to be enriched because that is the fissile material. So for light water reactor, the percentage of uranium-235 has to be 3 to 5%. So it is slightly enriched. But after removing it from the reactors, after utilization in the reactors, in the first cycle, you will find that 96% original uranium is still present in the fuel. And it contains now 1% plutonium also. Not 1%, little less than that. And 3% fission products. And little less than 1% U-235 is still present in the spent fuel. This plutonium is actually man-made material. It is not found naturally. So it is converted from U-238 to plutonium-239 in the reactor, nuclear reactors. This is the cycle, or one through fuel cycle. After mining, milling, conversion, enrichment, since it is for the light water reactor, enrichment is necessary. The fuel fabrication, it is the uranium dioxide, then light water reactor, and finally it is sent for the interim storage for a longer time till the short-lived radionuclides get decayed completely. Then it is discharged in the repositories, basically because it still contains highly long-lived radioactive materials. And of course, this reactor has to be provided with the cooling, and it can be used for irradiation of some materials like cobalt. Cobalt 60, which is used for irradiation purposes, is generated in the reactors only from cobalt 59. Then it is twice through fuel cycle. Now in this, as we have seen that spent fuel still contains very good amount of uranium. I mean uranium-235. It contains plutonium also. So in this twice through fuel cycle, reprocessing is adopted for extraction of the plutonium and uranium, which can be reused. So spent nuclear fuel is reprocessed for recovery of uranium and plutonium, which can be reused and recycled in the reactor again. And recovered uranium and plutonium can be suitably fabricated as MOX fuel in light water reactor. MOX fuel for utilization in light water reactor. But condition is that after secondary radiation, means after using as MOX fuel in the light water reactor, this is not good for recycling anymore because plutonium gets degraded. Its isotopic composition, isotopic characteristic change so much that it is no more usable for the nuclear reactor purposes. So it is not used further and discharged as in the case of once through cycle. So it is twice through fuel cycle. First was once through, this is twice through. The fuel you are recycling at least once, so it becomes twice. And major reason for recycling is that the SNF still contains 96% uranium, and PU also. That is reusable energy source material. And other advantages are that 17% more utilization of natural uranium is possible through MOX fuel option, and waste volumes are reduced greatly by over 80%. And similarly, radiotoxicity present in the spent nuclear fuel is reduced over 90%. These are the advantages twice through fuel cycle. Slides. This is the diagram for twice through fuel cycle. You will find that after the light water reactor, the interim storage, the spent fuel is taken for thermal reprocessing. Then plutonium, whatever is extracted out, that is sent for MOX fuel fabrication. Uranium is sent for conversion, then enrichment, and then for MOX fuel fabrication. And this MOX fuel can be again reused in the light water reactor. But after the second utilization, this has to be sent for interim storage and final waste disposal in the repositories. Slide. Now the closed or recycled fuel cycle. This is something that we are practicing in our country. And this is practiced in other countries like France, Japan, China, Russia also, as in India. So this aims at effective utilization of fissile material through multiple recycling, thereby reducing hazardous nature of radioactive waste and also recovering minor actinides and other radiotoxic elements. We'll see in the subsequent slide that this spent fuel basically contains many fission products, many radiotoxic elements, which have application in the various fields for irradiations, plus in the defense or the space applications also. And there are minor actinides, which are also man-made material. So they have many applications for space applications also. So in this closed fuel cycle, apart from recovery of plutonium and uranium from the spent fuel, we try to recover those radioactive elements also, like cesium, strontium, and so on. We will see in the subsequent slide, so that they can be used for various purposes. So that is the advantage of closed fuel cycle. And whatever plutonium we are recovering from here, that is to be used in the second stage of reactors. That is what we saw in the other, the light water reactor, it cannot be used. But in the fast breeder reactors, we are having test breeder reactor at Kalpakam, and prototype fast breeder reactor is coming up at Kalpakam. Therein, those are called the breeder reactors, because whatever fuel you use, that can be breeded further. Plutonium, you are using uranium plutonium as fuel in the fast breeder reactor. But in the reactor itself, further production of plutonium as well as U-233 from thorium takes place. So that is called breeder, because rather than consuming the fuel, it produces more fuel. So that is why again it can be reused. You have used twice, you can use next time, then next time also. So it is called close and recycle, multiple recycling fuel cycle. Last two things are just for your information, that energy extracted from nuclear fuel in reactor is having the unit as gigawatt days per metric ton of heavy metal. Heavy metal is that uranium. So gigawatt days per metric ton, that is the unit. And burn up, when we actually utilize this fuel, it is utilized to a defined rating of burn up. So burn up is a measure of fuel depletion, that is fuel atoms, fission in percentage of number of initial HM atoms present. So that is the burn up. फूल ज्यादा हो रहा है. Yeah, next slide please. Okay, so this is the block diagram for closed fuel cycle, schematic representation. Other things remain same: mining, milling, enrichment, fuel fabrication, the nuclear reactor, then spent fuel storage, reprocessing. After reprocessing, again, whatever plutonium you remove, that can be used as fuel fabrication and reutilization in next type of nuclear reactors. And after reprocessing, the waste is discharged for vitrification, which is to be stored in the deep geological repositories. Yeah. We were talking about reprocessing, that is basically Purex process for extraction of plutonium, and byproduct is uranium. So the fuel bundle, whatever picture you have seen in the earlier slide, that fuel bundle is actually used in the reactor. More or less in the same geometry it is returned, because you see even after burn up, which can be in the range of around 7,800 to 30,000-40,000 hours. This fuel bundle returns as it is. So that is taken up for the chopping, that is chopped in the small pieces. Then it is dissolved in the nitric acid. Then through solvent extraction process, the plutonium and first the uranium and then plutonium are removed from the process liquids, and basically we use TBP there. So this plutonium and uranium are taken away by the organic phase in the TBP, and the H1O3 carries all the fission products along, which is coming as waste or called raffinate. And uranium and plutonium get separated using TBP. Then final, from this solvent, we recover the plutonium also as final product. So that is the proceed for process. The types of nuclear reactors. So we have in our country boiling water reactors. They are there at Tarapur. 2 units are there. Then pressurized water reactors or light water reactors we have at Kudamkulam. The pressurized heavy water reactors, that is our indigenous PHWR reactors, we have at several sites, like we have at Madras, Kalpakkam, Narora, then Kota, Kakrapara, and Kaga. Then gas-cooled reactors, these are still under development. I think only one country or so are having gas-cooled reactor presently. Then liquid metal fast breeder reactors. As I mentioned, we are having the test reactors at Kalpakkam, and the prototype is getting ready for commissioning at Kalpakam. Then small modular reactors. This is a newer type of reactor being researched or developed in the many countries. I think Russia has already developed some small modular reactors. The picture is for the Kakrapara Atomic Power Station, 700 megawatt Unit 4, which has attained criticality on December 17, 2023, Sunday at 117 hours, just about few days back. Now, this is the nuclear fuel cycle applicable for our country. So you will find that from the mines, after milling, the fuel is coming for conversion to oxide, then fabrication of the fuel fabrication as bundle, then utilization of the reactor, and reprocessing. From reprocessing, you are having plutonium for usage either in the light water reactor or in the fast breeder reactors, and the recovered uranium can be sent for further conversion. The waste management, from the reprocessing we take the waste which is to be stored as the vitrified waste product before it is to be discharged in future in geological disposal, DGR. And of course, from the reprocessing, we are having the byproducts, those radionuclides, which have application in medicine, agriculture, and other industries. The purpose of this slide is to show that nuclear radioactive waste, the radioactive waste what we are talking about, is actually generated in the reactor. It is generated in the reprocessing. And of course, some small portion is coming out from the mines as well as from the fabrication plant also. And of course, final product comes from the waste management. So we had seen the picture of fuel bundle. Now let us see the spent fuel character. The spent fuel has, as we have seen, uranium and plutonium, which we get extracted in the reprocessing plant. Plus, it has the fission products. Now, fission products are like cesium, strontium, krypton, technetium, then transuranics like neptunium, americium, curium, and so on. So many fission products are there which have many applications for the industry, for the medicine, or the defense purposes. So, leaving this spent fuel as it is without any usage is perhaps not as correct as making an attempt for recovering not only the plutonium or uranium, but also these minor actinides. This neptunium, americium, and curium, they are called minor actinides. Minor actinides because their concentrations are very, very minor, very, very small. But still, if you recover them, they are really very useful. So, that is the strategy we have adopted for the nuclear fuel cycle. Now, these sources of radioactive waste, as I mentioned, the radioactive waste is generated in the nuclear fuel fabrication, the reactor operation and maintenance, then during spent fuel reprocessing, the nuclear research laboratories, isotope productions, facilities, and also the isotope users. Wherever those radioisotopes are used, either in the healthcare hospitals, in industries, or for the agricultural purposes, there also nuclear waste is radioactive waste is getting generated. So that has to be handled. That has to be properly contained and stored. We'll see the processes one by one. Of course, in today's lecture, it will not be possible. We'll cover some of the part of waste management in the other lecture. So the waste management activities, this is just one plant's picture I am showing you. Activities comprise of the waste immobilization. Basically, whatever radioactive waste is there, that has to be immobilized. Means that has to be stored in such a way that it doesn't move out. Then effluent treatment, whatever effluents are there, before they are discharged, they are to be brought within the safe limits, within the permissible limits. So effluent treatment plants, decontamination, whatever equipments are there, whatever materials are there, they are to be decontaminated for utilization or further usage. And the radioactive solid waste management. The waste, whatever is getting generated at the various facilities, is in the three stages. That is, in the solid form, liquid form, and gaseous form. So, whatever solid waste is there, that has to be also handled procedurally, carefully, safely. So, that is the part of waste management. Now, the principles of radioactive waste management. The principles adopted for waste management. The basic three principles are there, that is delay and decay. So there are some short-lived radionuclides like iodine and argon. Argon has half-life of just less than 2 hours. And iodine 131 has half-life of 8 days. The meaning of half-life, I think, has been already covered in the previous lecture. As you know that the radioactivity present in the source that gets reduced to half in a period of time, and that period is called the half-life of that particular substance. So as I said that this iodine 131 argon, but there are many others which have very short life, short half-life. So if we just allow them to delay and decay, so in due course of time, that will get decayed completely. Means that will not be harmful after that certain period of the time. So the first strategy is you delay it, store it in a room where it is not harmful to the people or to the system, and allow it to decay completely. The second formula is dilute and disperse. That is for low level waste. Low level waste, as per the limits, it is required to contain very negligible amount of activity. So you first ensure that low level waste, whatever you have, that is removed, or a radioactivity is removed from that to a large extent, to a acceptable limit, and thereafter you dilute it and disperse it. in the environment as per the limits set up by AERP or by the authorities, regulatory authorities. Then comes the concentrate and contain. Now this ILW and HLW. ILW is an intermediate level waste. HLW is high level waste. As we had seen the low level waste, we have ILW and we have HLW. These are another categorization of the waste. One was the form of the waste, that is solid, gaseous or liquid. Another is as per the radioactivity, they are categorized as low level waste, ILW, intermediate level waste, or the high level waste. So ILW and HLW, they basically contain lot of activity. So they cannot be, just disposed of like that. So they have to be vitrified, they have to be solidified in such a way that they can be safely stored. So for that, requirement is that they are concentrated, their volumes are reduced, and then they are safely contained in a proper method. So these are the three principles of waste management. Now, another dimension we have added to these three principles is the recycle and reuse. Other three things remain same: delay and decay, dilute and disperse, concentrate and contain. The fourth dimension that we have added is recycle and reuse. So whatever useful radioisotopes are there, materials, they are to be recycled, means they are to be separated from the high level waste and then they are to be reused. That is the methodology we have adopted and we are working on that with great satisfaction. Now this is classification of radioactive waste. This classification is done by IAEA. So there are three states, as I had already mentioned: liquid, gaseous and solid. Then they are categorized at category 1 to 5 or category 1 to 3 and so on. That is as per the activity present. When the category increases, its activity is increasing. The very low level liquid waste, say category 1, will contain activity as low as less than minus 10 to the power minus 6 millicurie per liter. That is negligible actually. At the bottom of the table, you will see that another equation is given, that is 1 curie is equal to 3.7 into 10 to the power 10 becquerel. Curie is the older unit of radioactivity and becquerel is the new accepted unit of radioactivity. But we are having a simple formula for you. How do we categorize this waste? So low level liquid waste, when the activity is less than 1 millicurie per liter, it is called low level liquid waste. And it is as good as neutral. And neutral means it will not have any harmful effect if activity is less than 1 millicurie per liter. Then intermediate level waste, ILW, that is having the activity in the range of 1 millicurie per liter to 1 curie per liter. And we have seen 1 curie is fairly large unit in terms of becquerel. So 1 millicurie per liter to 1 curie per liter, that is the intermediate level waste. So if you have ILW, it is definitely having some radioactivity. It has to be carefully handled and processed in such a way that activity is removed and managed properly. Then high level waste, this is the case where activity is larger than 1 curie per liter. So radioactive liquid waste have been broadly categorized into three categories depending on the concentration of radionuclides. So in terms of activity, it is defined as low level waste, intermediate level waste or high level waste. Now we come to the low level liquid waste, low level radioactive waste. So we had seen the sources. It comes from the reactors, reprocessing plants, radiological lab, fuel fabrication and waste management facilities. The operating personnel, after completing their task, they are supposed to decontaminate themselves. They are supposed to wash their hands or feet and if needed their body, they are required to do that in the change room. So whatever change room wastewater is there, that is called the low level liquid waste. So basically that contains very small level of radioactivity. So it is low level liquid waste. So but as you see, people are required to take bath also at times. They are required to wash their hands or feet. So volume generated of low level liquid waste is high. Compared to the HLW, volume is very high here. Their activity is high, here volume is high. Activity level is very small, that is ranging from 10 to the power minus 4 to 1 millicurie per liter. And they are chemically treated. Chemically treated so that they are brought to a neutral state, that is less than 1 millicurie, and there are no or very low level of total solids, dissolved solids, or the suspended solids in the liquid waste. And what could be the contaminants in this low level waste? We are calling it low level waste. So though we are calling low level, it is definitely low level. Activity is negligible. It is as good as neutral, but still some activity can be there, a small percentage. So that could be of the order of fission products or the type of fission products like strontium, cesium, ruthenium, or the activation products like gold, cobalt, and so on. And it may contain alpha also, which is very negligible, less than 1 becquerel per milliliter range. But these kind of contaminants may be present in the low level liquid waste. But before it is discharged, it is definitely seen that it is brought within the safe permissible limits as per AERB guidelines before it is discharged into the environment. What is the process? We will not discuss the process today. We'll have to leave something for the next lecture due to paucity of time. So now you see the general strategy for radioactive liquid waste management. The radioactive liquid waste management, that is volume, activity. These are the two things. You have to handle the volume, you have to remove the activity. Then the treatment, there are different processes, chemical treatment process, ion exchange process, or reverse osmosis process. There are types of processes. Of course, I will be naming them in the next slides. But after the process, what is tried, after the treatment, what is tried, then activity is precipitated and removed from the liquid waste. So it is brought out as the waste concentrate. Whatever activity is there, that is concentrated, precipitated and concentrated, then compacted. So activity remains, but it is compacted, its volume is reduced very, very much. So volume reduction factor is very high. That is volume in the beginning to the volume at the end. That is very high. So volume later on at the end of the process is small. In the beginning it is high, but activity level is more or less same. And the decontaminated waste, that is the liquid waste which is decontaminated, means reactivity has been removed. So their volume is same, but activity is brought down drastically. So decontamination factor DF, there A1 is higher, A2 is very, very small. So DF should be as high as possible, and VRF should also be as high as possible. That is VRF for the activity and DF for the decontaminated liquid waste. That is the strategy adopted for low-level waste treatment. Now, the treatment processes of LLW, an objective to minimize the activity discharge. So these are the processes, as I said: chemical treatment, ion exchange, RO, UF, centrifuge, filtration, and evaporation. Basically, in the process, it is precipitated, then in the centrifuge action, by centrifuge, the concentrates are separated from the liquid, then they are filtered and evaporated, made compacted. These things we'll leave for next class. So concentration of radioactivity is a smaller volume, and decontaminated stream discharges with minimal activities. Concentrate cementized and disposed at RSMS. Okay, so whatever activity is there, that is concentrated, compacted, then it is cementized, means it is mixed with the cement and then safely stored in our storage sites, in the deep trenches or in the containers. This table also has been discussed in the, no, this slide has been discussed partly in the previous lecture. I've just brought in this information here again to remind you that 1 curie, as I said, is equal to 3.7 into 10 to the power 10 becquerel, and becquerel is nothing but 1 disintegration per second, that is becquerel. And you see the so many radioisotopes, and they are having so many applications. That is, you see cobalt, cesium, strontium, radium, uranium, of course, radium. They are having applications for the radiotherapy, brachytherapy, and so on, or space application, polonium. Then, of course, uranium and thorium, this can be used for the nuclear fuel, as the nuclear fuel. And half-life, corresponding half-life is given in this slide, just for your information. And you see cesium-137, which is present, as I said earlier, as fission product. So if we recover cesium-137 from the high-level waste, it has application from brachytherapy for blood irradiations, sterilization of medical products, food irradiations, hygienization of sewage sludge, and so on. Now the next topic that we'll cover in next 10 minutes is contamination and decontaminations. So contamination is the presence of a radioactive material in any place where it is not desired, and essentially in any place where its presence could be harmful. I think it is understood. And let's see this drum. This drum contains radioactivity. It is marked with this symbol. The symbol means it is containing some radioactive material. And when it is containing, it is designed in such a way that on the surface of this drum, radioactivity is negligible. There is no harmful field available on the surface of this drum. It is free of any contaminations. Now, supposing there is a spill, there is a leakage from this drum. I mean, this drum is not just a drum. This drum must be containing another container with proper sealing. But somehow, if something spills or leaks, which is not really likely to happen, but supposing it happens, so you will find radioactivity on the surface, you will find radioactivity on the floor. So it will become a contamination. So because now the radioactive material is there on the surface where it is not desired, where it is not supposed to be there, and it is going to be harmful. So that is contamination. And contamination, how do we decontaminate? That is the picture, of course, here, but we'll see in the future, next few slides also. Now, what is the difference between exposure and contamination? So, if there is a source, radioactive source, and if a person is passing through near the source, from the field of the source, then there is an exposure. Okay? When X-ray is taken, there is an exposure. So exposure is there, means that person is definitely receiving some dose, but it is happening only as long as he is present in the field, or as long as that source is, there to give the field. If you are away from the source, or if the source is properly sealed, then there is no exposure. After the operation, you come out, you are quite clean. You are completely clean, in fact. And there is no contamination. There is no any harmful effect later on, because that is just an exposure. You have received a dose, that is end of it. But what happens in case of contamination? Contamination present on your clothing, contamination present on your body. So there is an activity on the body, on the clothing. You are not only exposing yourself continuously further, you are exposing other also, whoever comes in contact close to you. So that is external contamination. Internal contamination, somehow supposing activity is there inside. That can happen. That can happen by either injection, or by swallowing. Okay, so that is internal contamination, means some activity is there within the body. Then your organs, body organs at risk, at harm. That is internal contamination. So exposure to radiation source is external. Contamination possible internal or external. This is just another representation of the same exposure versus contamination. When you are passing near the source, you are getting a dose, you are getting radiation, that is external contamination, external exposure. But if you are contaminated, you are continuously carrying some radioactivity on your clothing or on your body, and you are radiating, in fact, you are exposing others also, if they come in close with you. Or if some activity goes inside, the body, then that is internal contamination. If something goes into the lungs by inhalation, then you are exposed internally. Your organs are at risk. That is internal contamination. So, how do we control contaminations? Contamination, disposition of radioactive material on surfaces that are undesirable. We have seen that. This may lead to external or internal hazard. We have seen external hazard, radiation field increases. Internal hazard gains entry into the human system. Internal hazard means some activity gains entry into the human system. That can happen either by ingestion, inhalation, or injection, like your corona jab injected. Inhalation, if something is there in the air, you inhale it. Injection, you swallow it or you absorb the radioactivity from your skin. So, types of contamination, it can be loose, it can be fixed, but loose contamination is not allowed. In our plant, we make sure that there is no activity in the air. We have continuous air monitors. Continuously, we monitor the air so that there is no radioactivity in the air, because loose contamination is very risky. If alpha source goes into your body, your organs are continuously at risk, continuously getting a dose. So contaminant, what is the type of contaminants? It can be alpha emitters, it can be beta gamma emitters. Fixed contamination, of course, there are limits. Within that limits, if you are there, it is all safe. Now, contaminants may result in personal external exposure and or internal exposures. Personal external exposure could be due to the deposits of contaminants in or on the surface. Personal internal exposure may be due to inhalation of air activity or resuspended activity, skin absorption, or inadvertent ingestion. During any radioactive work, contamination cannot be completely overruled. Contamination control is affected by monitoring of the contamination, use of protective devices, and decontamination. So I think it is very simple. As I said, we have continuous air monitors. So radioactivity can not be overruled. You have to control it. You have to take full care so that there is no contamination. You use monitoring methods. You use instruments for that. You use protective gears for that, protective devices, and you have to keep on decontaminating the workplace. External exposure hazard does not lead to any contamination hazard to the externally exposed individual. Clear, na? External exposure is external. There is no continuous contamination hazard. There is no internal hazard. But while internal contamination hazard would lead to certain radiation exposure of the internally contaminated individual. Simple, if any contamination goes inside the body, you are getting exposure continuously internally. Now decontamination, just another 5 minutes. Decontamination is removal of contaminants from the unwanted locations. As I said, supposing that drum gets contaminated, you have to decontaminate it. Decontamination is one of the valuable means of controlling transferable contamination. Personal decontamination is normally accomplished by using mild soap and lukewarm water. And medical decontamination is to be handled professionally by the experts. Methods of decontamination, decontamination techniques. This is for the professionals actually. Okay. So if any contaminated person is found, it has to be monitored. We have to check the activity level But whoever is doing that, he has to be fully protected. He has to wear all the protective equipment, personal protective equipments. Then, using the instruments, we can check the radioactivity. Then his external clothing should be completely removed. And by removing external clothing, substantial amount of radioactivity is removed. You'll find here the field was being shown very high. That is, I think, reduced substantially here. Then once he is given bath with water, then lukewarm water, then soap, etc., etc., you'll find that activity is removed from the body. Now it is present in the water or on the surface of the bathtub. Remember, when we clean something, we clean ourselves, but the dust is collected by the mop. Dust is collected by the duster. Dust doesn't go away. It is just transferred from one surface to the other. So that also has to be handled carefully. You cannot discard that in the environment just like that. This water, the soap water, this is the now low level liquid waste. So this has to be properly treated, properly handled. So decontamination, it is essential for keeping exposure of radiation worker as low as reasonably achievable. Decontamination methods would be helpful for reducing the level of contamination. By carrying out the decontamination during normal operation, the spread of contamination is checked. The area, equipment, and personnel are kept cleaner and hygienic. Overall objective of decontamination is to improve safety and protection of plant, person, and environment. So it is important. Why decontamination is important? It is the overall objective is to improve safety and protection of plant, person, and environment. During normal operations, decontamination is considered as a practice. Okay, as we work in the kitchen, we wash our hands after completing the work. Same way, when we work in our plant, afterwards we should clean the floor, we should clean the equipments, instruments, we should clean ourselves. So that is a part of the work practice. But while during radiation emergency situation, decontamination is considered as a countermeasure. Okay? And during emergencies, it is a countermeasure. Someone else is radioactive, someone else is contaminated, he has to be properly given treatment, bath, etc. Decontamination principles, removal of contaminations, decontaminations, order of decontamination, less contaminated area to highly contaminated area. As we know, when we clean our room, we always go from the cleaner section to the non-cleaner section. We don't go other way around. Then wherever dust is high, we will carry it to the non-dust area. We always clean from the clean side to the unclean side. So same way, less contaminated area to highly contaminated area, it should be done. Types, personal and the surface decontamination, sequence of operation, water, warm water, detergents, mild reagents, chemical agents. Radiotoxicity depend on the contaminant radionuclide, type, energy, and half-life of emissions. I think that is clear. We have so many radioisotopes, they have different kind of energy, they have different type of half-life. Okay, their natures are very different. They can be alpha emitters, they can be beta emitters, and so on. So they are unique in their character. So that toxicity depend upon that contaminant. Surface decontamination governing limits are higher. Personal decontamination care to avoid skin, facial, and hair treatment. Basically, you have to be careful about the person getting harmed, either on skin, face, or hair effects. Now, these are the personal equipments. personal protective equipments we use in our plant or we should use in case of any emergencies. If any emergency is there, that can be CBRN, that can be radiological or chemical. Proper personal protective equipment should be used before we take up the work. Then there are portable personal decontamination units. They are portable, they can be assembled at site for the giving bath, for giving the proper care, the treatment. And remember, then these are the water tanks, portable, foldable. So wherein whatever water is there, that cannot be thrown just like that in the environment. That also has to be properly stored, brought to the specific site for effluent treatment. Then this mass decontamination, the showers are there, which can be arranged at the side. But remember again, this water, whatever but wastewater is there, that has to be stored in the proper tubs and given for the site for treatment, effluent treatment before it is discharged. Lastly, before I say thank you, just for your information, this glass sphere, whatever you see, that is the size of the fission products, high level waste. The complete family for the lifeline if you use the nuclear energy. A complete family if you use nuclear energy for the lifetime, then total vitrified high level waste that is generated is equal to this mass of the sphere. The glass sphere which can be held on the palm represents the amount of vitrified waste arising from lifelong use of nuclear energy by an average Indian family for all its electricity needs. That just for your information. When we talk about the clean energy, why nuclear energy is clean? Because this is the only amount of the waste generated when a complete family uses nuclear energy for all electrical needs for the lifetime. Thank you. Before I close, friends, we are coming to the close of stage one. Of course, we have 2 weeks to go. We have 2 lectures, or rather 3 lectures scheduled next week. And in the first week of January, we have 3 sessions. I'm thinking that we will have first session for the question answer session. And on 5th, we are planning a demonstration by NDRF, field exercise and demonstration by NDRF. And we will try to live telecast that, live broadcast that. Whoever is physically present here in Mumbai, he can come for the, first-hand information, first-hand demonstration. And though we had scheduled the examination on 5th of January, we thought that we'll have it little later. So I have a request that for the question answer session, if you have some questions, you can please email to us. We'll take up them for discussions in the session, and we'll have it as open forum, wherein some of the questions can be asked at the time of the session itself, during the session itself. So thank you once again, and wish you all very, very happy New Year. Merry Christmas. Thanks.